Welcome to the final installment on our series on sum and difference formulas. Last time we were able to get ourselves acquainted with our formulas and use them to compute exact values of trigonometric functions such as 15 degrees, 105 degrees, call it that sort of thing. So what I want us to do now is start to use things a little more abstractly. I want to prove some more identities, maybe some in specificity and then some in generality, maybe some more commonly used ones, more popular ones, and then some less popular ones. So let's have a look at it. I claim to you, this is a theorem that I think is a theorem. I don't know if it's formally called a theorem, but the claim is that every of the 6 trigonometric functions, you can get to its cofunction by applying the transformation f of pi over 2 minus x. So in other words, the cosine, being the cofunction of sine, is sine of pi over 2 minus x. The tangent, being the cofunction of cotangent, would be cotangent pi over 2 minus x. So each of the 6 trigonometric functions can all be made into its cofunction just by applying the same transformation each time. And you could verify that individually by graphing. If you were to apply the transformation for sine of pi over 2 minus x, well, that's the same as sine of x, negative x plus pi over 2. So I've got a flip across the y-axis, a shift to the right by pi over 2, and you could do that for each of the 6 trig functions, and you'll always find its cofunction after you do the transformations. Well, for those of us who don't like drawing that much or aren't that confident in our drawing abilities, another way you could go through and verify that each of the trig functions has that as their cofunction, you could do what I've done here. I can show, and did show, that the secant is actually its cofunction, cosecant, with the transformation pi over 2 minus x. And I did that by using the difference formula. Right, recognizing that cosecant is 1 over sine, I wrote 1 over sine of pi over 2 minus x, and applied the difference formula for sine. So I got 1 over sine cosine minus cosine sine, and sine of pi over 2 and cosine of pi over 2, well, that's something I can evaluate. Right, sine of pi over 2 is 1, cosine of pi over 2 is 0, and so after all of this evaluation, I just have 1 over cosine minus 0. 1 over cosine, and that is in fact secant. And if you really wanted, you could do this for all of the trig formulas. I won't stop you. You can do it. I trust that it's true. I've done it before, I'm pretty sure, and I think it worked. You're welcome to try me, though, if you're not so confident. But that's how we get at the cofunction identities. So now we have access to 6 more identities. Sine is equal to cosine of pi over 2 minus x. Cosine is sine of pi over 2 minus x, etc., etc. That's exciting. But for those of us who are less excited for that and more excited to prove other identities, well, I've got this to remind you about. If you're wanting to prove something, an equation is an identity, there's a few strategies for you. Right? You start with the more complicated side, take that as a separate expression, simplify that one expression one at a time, and hopefully end up with the other expression, not having to switch over. And also remembering that you can use any existing identity you have access to. The Pythagorean identities, the sum formulas, the difference formulas, the even-odd identities, right? The sine of negative x equals negative sine x. You can use that if the situation ever arises that you might need to. So using existing identities can save you a lot of effort because you don't have to reprove things that have been proved. It's a very mathematical thing to build on existing knowledge. And of course, if all else fails, rewrite everything you see as sines and cosines and start over. See if you can make any further progress with just sines and cosines on your hand. So here's an example, something I have to illustrate what I mean here. We saw this in the application of the trigonometry, the trig sine and cosine waves. So I had phase cancellation and that sort of thing. I had two cosine waves that were out of phase and they were canceling each other out. Well, I made a claim there, offhandedly, that you take any two sine or cosine waves and add them together, and that end product is always going to be some flavor of sine or cosine wave. And maybe you smiled and nodded, maybe you humored me, but that's pretty serious. That's a very real claim. That needs to be backed up. And so what we're going to do today in this video is actually show that. Actually prove that I've got a sine wave and I've got a cosine wave, and I stick them together, I still get a sine wave. Obviously, I'm still making some simplifications here, some simplifying assumptions, but I'll get to that some other video. Here I just have a sine wave of some amplitude, a cosine wave of some other amplitude, and the claim is if I take those two waves and add them together, I'm going to get some third sine wave of some amplitude k and with some phase angle phi. Specifically, k is the square root of the sum of the squares. It's square root of a squared plus b squared. And phi is such that cosine of theta is this guy, sine of phi is this guy. I said theta there, sorry. But these are my conditions. And the way we would go about proving this is quite simply showing that this equation that we had in our theorem, that equation is always true, that equation is an identity. And we have a pretty good idea on how to do that, at least I hope. What we would do is we would just start with a more complicated sign, and the more complicated side here is this right-hand side, k sine of x plus phi. There's a lot to unpack here, right? Sine of the sum of two angles is going to be four trigonometric functions, right? It's going to be sine, cosine, cosine, sine. So starting with the right-hand side, k sine of x plus phi is equal to k onto the product as the product of sine x cosine phi, cosine x sine phi. And then remembering to evaluate sine and cosine for phi, I've got k sine x, a over that stuff, plus cosine b over that stuff. But then remembering that k equaled that stuff, and distributing, I've got that stuff and that stuff canceling, that stuff and that stuff canceling. So I've got sine x times a, cosine x times b, a sine, b cosine. That was the left-hand side, right? That's what we started with. So we have shown that this equation is an identity. This equation is always true. And so the takeaway is if you have any sine wave, any cosine wave, with the added assumption anyway that they're in phase, we'd have to do a little more legwork to get them out of phase. Maybe we'll do that some other time. But if they're in phase, we have definitively shown that they do add together to be a sine wave. And, you know, there's something to be said about that. We can exult in our accomplishments. And really, that's all I really wanted to do in this video, is to show that they can be used. These expressions and equations can be used to show still more useful things. They have value more than just in and of themselves. There's more to be done than just evaluating the tangent of 15 degrees. Not to say that's not useful, but there's more that we can do. So let's kind of take stock of where we are now. We're able to use sum formulas and difference formulas, use those to compute more and more values of all the trig functions, and also use those to prove more and more identities, kind of growing our knowledge base here. Well, it shouldn't surprise too many people then that in the next section, when we add on still more identities, we will continue to use those identities to find more and more values, prove more and more identities. So look forward to seeing you in the next series where we get to do even more with trig functions. Look forward to it. Have a good one.